Previously, we've been using the metric stairs as a tool to help us convert from one unit to the next within the metric system, or one unit to another. Hopefully you've been able to do those in 3 seconds or less by just copying the number, find deci, and move deci. Now we're going to move to when we make measurements with the metric system, how do we know how many numbers to jot down and record in our measurement? So this is page 6. Rulers, the final figure. Most certainly a throw out to the final frontier of the Star Trek series. And if you need some excuse to get out doing some chores, perhaps you could toss out that in your Physics B lives, there'll be some Star Trek references that can benefit you for your knowledge of. So, sorry, parental units, guardians, I can't do the dishes or mow the lawn. I've got some Physics A homework to do by watching hundreds, thousands of hours of Star Trek related material, whether it be the original series, Starship Enterprise with Captain James T. Kirk at the helm, or Enterprise D with Captain Jean-Luc Picard at the helm. Today, though, ruler's the final figure, the figure referring to the last digit or the last number. The following measurements were provided for the height of this paper: 27 9/10 of a centimeter, 27 9,400 thousandths of a centimeter, 27 94 hundredths of a centimeter, and 27 centimeters. If a metric ruler like ruler B below was used, the accurate recorded measurement is 27 94 hundredths of a centimeter. Why is this the case? Pause this media presentation so you can give yourself some time to jot down some keywords as to why the width of this paper, using a ruler that would look like this, we would record as 27 94 hundredths of a centimeter and not these other measurements. Looking at rulers, I mentioned we have these accepted values, or these targets. This particular ruler is using decimeters as its main target. There's no accepted values in between. This has one level of accuracy. This ruler in centimeters also has one level of targets. So it too has an accuracy level of 1. This in millimeters has not only these centimeters, remember 10 millimeters in 1 centimeter, not only does it have this level of accuracy, but has another level of accuracy between the 2 and 3 centimeters, or 20 and 30 millimeters is listed here, but these are the millimeter marks. The first and the second rulers on the page here have one level of accuracy, whereas the next ruler has 2 levels of accuracy. Very similar image. This ruler written in centimeters, 1 set of targets. This ruler also listed in centimeters, 0 to 1, 0 to 2 is 1 set of targets. And then in between the 0 and the 1, you have the millimeters. So there's 2 levels of accuracy, or 2 levels of accepted values here. And be careful, this ruler has the same amount of accepted value. These are centimeters in between 0 and 1, 1 and 2, just matching above here. It just so happens the ruler is printed saying this is 0 millimeters and 10 millimeters, so counting these. This has 1 set of targets, 2 sets of targets, 3 sets of accepted values or targets. The rulers you'll be using in this class have the centimeter divisions and then the tiny little millimeter divisions in between. If I were to record a measurement for the length of this nail, I see that the nail goes accurate past the 1, the 2, the 3, the 4, the 5. It's accurate past the 6 centimeter mark, but it's not accurate to the 7. So it does hit the 6, so I'm going to jot down that the measurement is accurate to a 6. I do have another set of targets, so I put a decimal here, so I'm doing another level of accuracy. And if we look at this expanded view here, these are the millimeter marks. I'm accurate past the 1st, 2nd, 3rd, but not the 4th. So I'm going to put a 3 there, as I'm accurate past the 3rd, or the 1, 2, 3, yes, 4th mark. I'm not quite accurate to the 4th, so that's why I've put a 3. Now I don't have any more accepted values or targets in between the millimeter lines here. It'd be very, very, very difficult for the human eye to see. So what I do is I make a guess. Maybe this is a 4, maybe it's 5. It's a guess because we can't break down visibly with our eye any more accurate divisions here. So it's a guess. And sometimes the term guess makes people uncomfortable to say that we guess in science. But the guess is very powerful. So whatever guess I put here, maybe I put that this is a 4. 6 34/100ths of a centimeter. Scientific data, sadly, outlives our scientists, ourselves. And so we want to make sure that the data we record is able to be understood by people who don't have access to the tools that we use to measure. The key in understanding what type of instrument someone used is looking at the final figure. So the final figure is a guess. This 4 being the last digit recorded is letting someone know that these are accurate measurements, that there were targets on the measuring device for a centimeter and for millimeters. The last digit is very powerful in saying this is a guess. We have a set of data here that are measurements. Remember, the key in our measurements is actually the final figure. This right here is the final figure in this measurement. Final figure here, final figure here, here, and again here. The final figure lets us know that this was a guess. This then allows us to recognize the numbers preceding the guess. Those numbers are all accurate, meaning there was a set of accepted targets, values that have been agreed upon and established as the accepted values. This number, or this data set right here, lets us know there was only one set of targets that were on the ruler used to make this 9-meter measurement. This right here lets us see that there is many more targets, well beyond the millionth of a decimal place on the accuracy of the ruler. So much more accurate with more targets. This measurement here, this data, that's quite incredible. There's no way a human was able to differentiate between the tiny lines, and I'm not sure how accurate our laser measuring devices are, computers, in getting to this level of detail and accuracy as well. This 2.00, just want to elaborate on the level of targets that we have here. A measurement of 2 meters for a typical doorway height might be recorded as the following. And they all read 2 meters, 2 meters, 2 meters, 2 meters, 2 meters. But bearing in mind that the last digit is a guess, that 2 is a guess. This 0 is a guess. This 0 a guess. This 0 a guess. This 0 a guess. But the final figure showing a guess, that means all the digits preceding the guess are accurate, meaning there was a set of targets that an observer used to make their and record their measurement. This 2 is itself a guess. That means someone just estimated, just looked at the height of the doorway and said, maybe about 2 meters. This individual had a meter stick, but it was probably only as tall as 1 meter stick and had one accurate mark to show a meter. This one right here had 2 sets of measurements or accurate targets on there to show that the 2 is accurate and that it was right on the line of 2, that there was another set of targets showing more level of accuracy. And again, this is quite an extensive level of accuracy. The take-home message here is the final digit, the final figure, is a guess. That's not to make someone think that science is all about guesswork and it's not black and white. Science certainly isn't black and white, but there are a place for guesses. This place, the guesses allow us to say the numbers preceding the final figure are accurate. There were targets in place that the observer could make a measurement. Let's have you practice letting a person know how accurate your measurement device was. If we use the pen, careful, the shadow here looks like it's going off the ruler, but the actual pen tip here, all the way to the end. Record your measurement of this pen in this space right here. Little shout out to Benson Hegeman, who's the student who gave me this pen at the conclusion of the wonderful first ever play at Ridgeline High School of Legend of the Riverhawk. So record your measurement here. We are accurate past the 7, not quite the 8, so the 7 is accurate. Now I'm going to go to the next set of measurement marks. So I'll go to a decimal, and it looks like we're accurate past the 1, 2, 3, maybe the 4, 3, and then a guess. And of course, record that the units are centimeters. If you have a 4 here, that's fine. Take a moment now to consider why we will never ever have a measurement where we use repeating decimals. Maybe we have decimal 7, 6 with the bar, meaning repeating. This is something that we won't ever use when we record measurements. Take a moment to try and think about why this would be in light of what we've learned about the way in which we record accurate measurements. Pause the video and think about why we don't record measurements or calculations using repeated decimals in physics. It all goes back to the concept that the last figure is a guess. The final figure is a guess. If you have a number with a repeating decimal, that means that you are forever accurate. And it is incredibly difficult, dare I say absolutely impossible, that you could have a ruler that has every set of accepted targets on there. You would just see a strip of ink and not being able to determine that increased level of accuracy. So we will not be using repeated decimals in our measurements or calculations. So certainly you cannot have a ruler which has all of the accepted values. The following clip from Minute Physics is a wonderful things that make you go, The question you're going to be asked to consider in this short video clip is, do you think A or B? Do you think that there are more numbers between two single set of digits, say the number 9 and 10? Do you think there's more numbers in here than all the numbers that make up infinity? For the bragging rights, lock in your answer, A or B.
Today we're going to count infinity. Now, counting may seem elementary, like when we say that we have 5 sheep, we really mean we have 1 sheep for every number from 1 to 5, and 10 sheep means 1 for every number from 1 to 10. So we say that 2 sets have the same number of things in them simply if you can draw a line relating every item in one set to something in the other, and vice versa, exactly once. They're partners. It's the same when we say that 2 plus 1 equals 3, or 3 doesn't equal 4. We're just describing the lines you can draw to relate one set of things to another. But either way, counting sheep is boring. That is, unless you want to count infinitely many sheep. Like, if you had a sheep for every number between 0 and 2, would that be more sheep than if you had one for every number between 0 and 1? Nope, because you can relate every number between 0 and 1 to its double, giving you every number between 0 and 2. And if you want to undo, you can just divide every number between 0 and 2 in half to get back all the numbers between 0 and 1. But there are more real numbers between 0 and 1 than there are in the infinite set of integers 1, 2, 3, 4, and so on. How on earth do we know this? Just draw some lines. For 1, draw a line to a number between 0 and 1. And for 2, draw a line to another number between 0 and 1. For 3, draw a line to a number between 0 and 1. And so on. But no matter what numbers between 0 and 1 we've drawn lines to, we can always write down a number between 0 and 1 that disagrees with the first digit here, the second digit here, and the third digit here, and so on. So this new number will be different from all of the other numbers we've drawn lines to. But we've already drawn a line from every integer, so there's no one left to be this number's partner. What's more, we can find an extra lonely number like this no matter what other numbers we picked, which means we can never draw lines from the integers to all of the numbers between 0 and 1. And this means that there really are more real numbers between 0 and 1 than there are in the already infinite set of counting numbers 1, 2, 3, 4, and so on.
Excellent. What I'd like you to do now is to spend some time pulling together your thoughts about rulers, the final figure, and why, if a metric ruler like ruler B was used below, the accurate recorded measurement is 27 9400 centimeter, no more and no less of decimal places. Pause the video, give yourself time to gather your thoughts and put them into your notebooks here. Pause the video to give yourself time to do that. Next, you're going to practice your measuring skills. Rather than having a ruler go to the full length of an object, here we just have arrows pointing to the space that you would assume something had been lined up to. You're going to record the measurement in the space below. Be sure to include units, yes, for every measurement, always. Do this for ruler 1, 2, 3, or in other words, A through W measurements. For more practice, on your Think and Solve page 13, item 9, we have more letters, L through U, that you can practice with. And to further sharpen your scores, you may notice down here on page 6 of the study guide, place for you to record a score. And this is if you'd like to go to this tiny.cc/final figure URL, and it's a little skills practice, drill and practice with a ruler that we'll see who the champion might be.